Hey, hello and welcome to today's GFG problem of the day. Hope you're doing well. Let's say today's problem merge two BSTs. Okay, so what the problem is saying is we'll be given two binary search trees. Okay, and what we want to do is we want to merge the elements of these two binary search trees and we want to return those merged list, right? Those merged elements in the sorted form. Okay, in the sorted form. Okay, so how can we solve this problem? Okay, so first let's see the brute force approach. Okay, so let's see the brute force approach. So what we are going to do is we are going to run and in order traversal, okay, of both these binary search trees. Okay, so so if we do the in order traversal of binary search tree, then we get the elements in sorted form. Okay, so what will be the elements here? So for example here, right, for this binary search tree it is going to be 2 3 4 5 and 6. Okay, and for this particular binary search tree, what it is going to be, the in order traversal, it is going to be sorted form 1 2 3 6 7. Okay, now we have two lists, right? We have two lists, that is L1 and L2. Okay, L1 and L2. Okay, now what we are going to do is we are going to take a resultant array or list. Okay, and what we are going to do, we are going to take two pointers, one for this, one pointer for this array, and one pointer for this array or list. Okay, and we'll compare each elements. Okay, so what we are compare. So whichever is lesser, we are going to add in the result, and then we are going to move the pointer. Okay, we are going to move the pointer. In this way, we'll compare the two pointers, and whichever is lesser, we will add into the resultant list, and then we'll increment the pointer for that array. Okay, so okay, so here, if you see what will be the sorted 4, 5, 6, 6, 7. So this will be the okay. I think I missed 3. So I'll add 3 as well. So this will be the resultant list. Okay. So this is the expectation. But what will be the space complexity here? The time complexity is it is going to be, for example, if there are n nodes, right? N nodes here and m nodes here. So the time complexity is it is going to be O of n plus m. And what will be the space complexity? It is going to be C. We are taking two lists, right? If there are n nodes here, so n one list, right? One particular thing, right? And this one for m nodes for this particular O of n plus m. And again, we have this resultant list as well. So it is going to be like this, O of n plus m plus n plus m. Okay, so this will be the space complexity. Okay, so this is a brute force. We can, I think, optimize further. Okay, so let's see. So the expected space complexity, it is O of h1 plus h2. Okay, plus the resultant, the space for resultant list, which is going to be n plus m. Okay, we'll see how we can achieve this. Okay, so let me erase this. Okay, let me write the expected space complexity again. O of h1. H1 is the height of binary search tree 1. H2 is the height of binary search tree 2 plus n plus m, which will be the resultant list. This is expected space complexity. Okay. So what we can do is, what we'll do is, instead of running the recursive in order traversal, we are going to run the iterative in order traversal. So what we're going to do, we're going to take two stacks, S1 and S2. Okay. Okay, so what we're going to do? So we'll first do, actually we are going to do the iterative in order traversal for both these trees. Okay, so what we're going to do first? So first we are going to um, iterate through this, right? We are going to, what we're going to do, we'll start from root and we'll keep on going till the extreme left. Okay, we'll keep on going till extreme left. So when we are going, so during that time, we are also going to insert into the stack. So here we're going to insert 5 and then we are going to move to the left of 5. Okay, we'll insert 3, then we'll move to the left of 3. Okay, then we will insert 2 and we'll go to the left, but we cannot go to the left because it does not have the left child. Okay, so we will stop here, okay, because it does not have any left child. Okay, so now we are done for BST1. Now we'll do the same for BST2. So what we'll do, we'll start from here. We'll add the node value, or node, sorry, not the node value. We'll add the node. Okay, and then we'll move to the left. We'll add 1 and we will try to move, but it does not have any left child. So we'll stop here. Okay, so now we have stopped here. Now what we're going to do, we are going to run a while loop where until these two stacks are not empty. Okay, so what we're going to do, so we are going to we are going to compare the top elements of both the stacks. Okay, so what is the top element here? For this particular, it is 1, and for this particular, it is 2, right? So whichever is lesser, we are going to pop that out. We are going to pop that out. So we got 1 here, right? We got 1 here. Now what we are going to do is we are going to go try to go towards the right. We are going to try to go towards the right. Okay, and start the like adding the elements into the stack, into this stack again. Okay, into this stack again. Okay, for this particular, but here, as you know, there's no right, so we'll stop here again. We'll stop here, and we'll also add this into resultant array, this particular one. Let's have resultant array here. Okay, we have added one here. Okay, okay. Now what we're going to do again? We'll take the compare the two elements, right? Top for S2, the top is 2, and for this S1 it is 2, right? So we'll pop out both the elements. We'll pop out both the nodes. Okay, so we'll pop out both the nodes. Okay, and we'll also add in the resultant this list 2 and 2. Now what we're going to do? What we'll do is, so what we got, these are the two elements, right? From BST1 and 2 from BST2, right? 2 from BST2. Now what we'll do? We'll try to go to the right again. Now for this particular 2, we're going to try to go to the right, but we cannot go right because there's no child. Okay, so we'll stop here. We'll stop here. For BST1, we'll stop here. For BST2, what we're going to do is we will go to the right. So here, the 2 is here, right? So we'll go to the right. Okay, so once we go to the right, now we got 3, right? Once we go to the right, so what we're going to do, we are going to go to the left of 3 again. Okay, left of 3 again. We'll try to go to the left of 3. So here, first what we're going to do, we got 3 here. So we're going to add in the stack. This we are adding in the stack S3, S2, right? 3 we added. Now we'll go to the try to go to the left, but there's no left here. So we'll stop here. Okay, we'll stop here. Okay, now again we'll compare the top of both the stacks. So what we have, the top of S1 is 3 and the top of S2 is 3 again. Okay, so we will, as both are same, we will remove them. We'll remove both of them. Okay, we'll add into the resultant list. Okay, resultant list. So what we have now, 3 and 3, right? So for BST1, we'll try to go to the right. Okay, so here is 3. For BST1, here is 3. So we will go to the right. Yes, we went to the right. We'll also add 4 over here. Okay, we'll add 4 over here first. Okay, this particular 4, and we'll try to go to the left. Okay, there's no left. We'll stop here. Okay, we'll stop here. For now, we'll do the same for this 3. Okay, we'll do the same for just hold on. Yeah, so for this particular 3. Okay, so we'll go to the right now, right? We will go to the right. So yes, there is this right? So what we're going to do, we're going to add 7 here. We're going to add 7 here, and then we'll go to the left. Okay, of this. We'll go to the left of this. So yes, we found 6 again. So we're going to add 6 here. Okay. So now again, we try to go to the left, but there's no left child, so we'll stop here. So what we're doing here is, first we are starting from the root. We are going to the extreme left. Okay, we are going to the extreme left. We are adding, while we are going to the left, we are adding into the stack. So once some element is popped out, okay, we go to the right child. It's right child. If there is right child, for that particular right child, we again go to the left, and we keep on adding those elements in the stack. Okay, I hope you've got this. You're getting this intuition. Okay, so now this is the state, right? So this is the state. Okay, so now again we'll compare the top of the 2 stacks, 4 and 6. So now whichever is lesser, we are going to pop that out. So 4 is lesser, so we're going to pop out. Now what node we have here? We have 4. We'll also add in the resultant list. Okay, 4. Now what we are trying to do, since we have popped this out, so we'll go to the right child. Okay, we'll go to the right child. So for this case, right, 4 is here. So there's no right child, so we'll stop here. Okay, now we have again. Now we have what? The top of the stacks, right? 2 stacks. One is 5, right? And this for stack 2, it is 6, right? So we'll again compare both these top elements, right? Again, this 5 is lesser. We'll pop this out. Okay, we'll pop this out 5, and also we'll add in the resultant list. Okay, now what we are trying to do, now we'll go to the right child of 5 first. So here is 5, right? Here is 5. So we'll go right child of 5. We'll add 6 here. So for example, 6 is the top. Just consider 6 as a top. We added 6 here in the stack. Now we'll try to go to the left. We'll try to process the left children of 6, but there's no left children, so we'll stop here. Okay, we'll stop here. Now we have top, right? We have popped this out. Now we have top elements 6 and 6. Both are same. So since both are same, we will pop these elements out. We'll add into the stack. This resultant list. So we have what? 6 and 6, right? We have 6 and 6. Now what we're going to do? We will try to go to the right child of 6. Okay, but if you see here, there's no right child. So we'll stop here, right? We'll stop here. same will do, try to go to the right child of 6. So here again there's no right child, right? There's no right child, so we'll stop here. Okay, now finally, right, finally, so this loop will break since S1 is empty. Now S1 is empty, S2 only one element is there, that is 7, right? So we'll simply pop this element out, we'll add into the resultant, and we'll try to go to the right element, right child of 7. So here we'll try to go to the right child of 7, but there's no child, so we'll stop here, and finally we'll have our resultant list ready, okay, to be returned. Okay, so this, and if you see, this will be the sorted list. Okay, this will be the sorted list. So I hope you've got the intuition. Now let's go to the code. I think you'll understand better. Before going to the code, I'll request you to subscribe to my channel, as a lot of effort goes in making these videos. Okay, thank you so much. So first I'll show the Java code followed by C++. Now there's some problem with the Java compiler here, so the second test is failing, but the code is absolutely right. We'll run the same code for C++ as well. Okay, there it runs completely. Okay, so let's write without much waiting. Okay, so what we are going to do now, we are going to write the util function first. Okay, no, first of all, what we are going to do, we are going to create two stacks first. Stack of type node s1 equal to new stack, right? This is the first stack, then this is the second stack, s2. Now what we'll do, we will now first push all the left elements, right? All the left elements of both the trees, BST, or both the binary search trees. So one would be root1 comma s1, right? And another would be root2 comma s2. Now let's write the util function. So void util node root stack type node s, right? And what we're going to do, while current also, or for example, here, let's name it current is not equal to null. Just add the element s dot add in this current, right? Not element, the node itself, right? And go to the left. Go to the left. Keep going to the left until you don't find any child. So here we are doing the same. We have added all the left children. Okay. In the stack for both this, right? For both these trees. We are done with this. Now what we'll do, we'll run a while loop. What we'll say? Empty, and then s2 dot is empty. So run this while loop till both these stacks are not empty. Okay. Now what we are going to do, we are going to compare top one, let's say top one, right? Top one s1 dot peak, which will give us the top element, right? It won't pop out, but it will give the peak. Okay. Top two s2, right? Now what we'll do, we'll compare top one dot data. Sorry, I think so. Yeah, top one dot data. If top one dot data is less than top two dot data, then what we'll do? Yeah, so now what we are going to do, we will add, first of all, let's take resultant list as well. List of integer result equal to new array list. So yes, so let's add resultant dot add top one dot data. Since top one dot data is less, so we'll add in the resultant list. Now what we'll do, we will also pop that top element, right? We also pop out the top element from the stack one. Okay. Now what we'll do, we will run this top one dot right element, right? We'll pass this util, pass this right element, right child of top one. Okay, okay, to the util function, and also we'll give s1. Now what we are doing here is, for example, right? For example, if this was a case 5, 3, and 2. Now we had popped this out, right? And here it is 6. And for example, let's say here it is, let's say, just take an example here, or let's say here it is 6. Okay, here it is 6, here it is 8, and here it is 7, right? So we just pop this out, sixth element, right? Now what we're doing is, we'll pass this 8 to the right, to the util function. Now what it will do, it will push on all the left children into the stack. Okay, it will try to push on all the left children into the stack. So that's what we are doing here. And so this is this util function, it is pushing all the left children to the stack. Okay, so that's what we did here. Else if, now if top two dot data, right? Let's copy this rather than it will save some time. Yeah. So what we are saying is if top one dot data or yeah. So top two dot data, if it is less than top one dot data, then add top two dot data in the resultant list, pop the element from or node from S2 and process the right child of S2, right? Of BST2. That's what we did here. Okay, else another thing is if both the popped out elements, right? If both the top elements, right? They are same. So what we are going to do, first of all, we'll pop out from both, right? These stacks. Now what we're going to do, we will add also into the resultant list, resultant dot add top one dot data. Similarly, resultant top two dot data. Okay, we are done here. We have added. Now we'll pass the right children. We'll process the right children of both the nodes, right? Of both, yeah. Top one dot right S1 and top two dot S2. Top two dot right dot S2. Okay. So yes, we are done here. Now what we're going to simply check is now, but when, for example, one of the stack got empty, right? But the other stack still contains. So we will write the code for example, if S1 is not empty, right? So we have to take care of this as well. So what we'll do here, we'll pop out node top one, simply will pop out node top one equal to S1 dot pop. Simply will pop out because there's no point in comparing the top elements. So we'll simply pop out, right? And we'll add resultant dot add top one dot data. We have added in the resultant list and we'll also pass, right? Util top one dot right? S1. Okay. So similarly, we will do the same. S2, S2 top. Okay. And finally, what we'll do, we'll return the resultant string. Sorry, resultant list. Return resultant list. Okay. So let's compile this. I hope you've got the code. Okay, there's some problem. Oh, okay. This colon list. It is compiled now. It will fail for the second test. Okay. As we know, I've already told you. The second test for Java, it is failing somehow. Situating. Yeah. Okay. I think they have fixed those test cases. I think they have fixed those test cases. Good. So yeah, it is passed. All the test cases are passed. I hope you have got the solution. Please subscribe to my channel, like the video. Let's quickly see the C++ code as well. Okay. So here, if you see, right, it's the same thing. We have taken two stacks, then we have taken util function here. So what the util function is going, it is pushing we are going to the extreme left, and while going to the extreme left, we are pushing all the elements to the or nodes to the stack. Okay. So we are doing for both the BSTs. Then we are running a while loop for both S1 and S2. Then we are picking or comparing the top elements of both the stacks, right? If it is lesser, if top one is lesser, then we'll add to the resultant list. We'll pop that node out and then we'll process the right child. So what it will do for the right child, it will process all the left children or the left subtree, right? Or the left children. Okay. Then we are comparing if top one is greater or right. So we'll add top two dot data, right? And pop and do the same thing, process the right child. If both are same, then we'll add to the resultant list both the elements, right? We'll pop the nodes out from the stack, both the stacks, and then we'll process the right children of both the trees. Okay. Similarly, finally, if if one of the list is still not empty, so we will pop that element out. We'll add in the resultant list, and we'll also process the right child. Similarly for stack to this we are doing. So this is a yeah, finally we'll return the result. So this is a solution. I hope you've got the solution. Now how it is better, let me quickly also explain this, right? So if you see, right, at both these stacks, the maximum space it will take, right? It is going to be O of H1 only or O of H2. So which is O of H1 plus H2. It won't hold all the elements, that is all the n elements, right? Maximum it will hold the elements okay, the elements equal to the height of the binary search tree. Okay, it won't hold at each time. It won't hold in the worst case all the elements of this of the binary search tree. That is why it is better of h plus n. That is we are able to uh, yeah, we are able to meet expectation of the space complexity here. Okay, so this is a solution. I hope you have got the solution. Thanks for watching. Please subscribe to my channel, like the video. Have a happy, healthy, and a great day. Thank you so much.